involved, about the learn-bloom filter problem. We'll talk about some other stuff. The talk will be part survey. In the middle, I'm going to break a bit and talk about some of the amazing things other people, including Piotr and his group, have done. And then I'll talk a bit about some more of my stuff, particularly queuing and scheduling, and sort of globally, I'll be talking a bit about the state of the area where we're going. And we'll see how much we get through. Please stop me and interrupt with questions or thoughts or ideas as you have them. All right, so a very simple motivating example would just be basic search. Okay, so suppose that you're given an array of n items sorted, and you have a query, and the typical thing that we think of doing is saying, okay, well, is this query in the array? Is this an element in our set? And so we have something like 7, and what we teach the kids in their first algorithm type class is to do binary search, right? Start in the middle, go higher or lower, and narrow the range, and eventually you're going to find the right element. And if there are n elements in the array, we know this will take log n comparisons at worst. All right, so seems pretty darn good already. What more could we possibly hope for? Okay, so an alternative approach that would use the idea of a prediction, right, is that, and the motivation here is to think of, a sort of prototypical example where we do search is like when we wander into a bookstore or a library, right? And if I'm looking for, Isaac Asimov, as I did when I was a kid, you don't start in the middle, right, when you're looking for Isaac Asimov, because the book's going to be in the A's, right? So you start over towards that part of the alphabet. Okay. So similarly here, if you were searching for a number, you might have a prediction, right? Now you're not going to use binary search, but you can start at the prediction and use a doubling binary search. So you go, if your number's smaller, you go 1 to the left, then 2 to the left, then 4 to the left, then 8 to the left. Eventually you'll go too far left, and now you have a range where you can do a binary search. All right, so this would be a way to do it that would take use of this prediction and is motivated by this sort of high-level idea of, you might have a guess of where to start. And so how can we compare these things? So binary search, again, is order log n. The prediction-based search is order log of the prediction error, right? Whatever the prediction error is, you're going to have to go to the power of 2 past that and then do a binary search. So the sizes of your range that you're going to deal with is at most 2 times the prediction error. So all this is order log of the prediction error. And here I'm sort of hand waving or sweeping under the rug that, of course, you also have to, in some sense, do this prediction. So that may add some time too. We're assuming, I guess, that that's essentially free. Right, so a terminology you're going to see, and this will pop up in other places, is we call this sort of solution, it's robust, because even in the worst case, the prediction-based search is still order log n. So in at least the asymptotic sense, it's not even worse than binary search, right? There is a different constant factor. It's going to be a higher constant factor, but it's still a logarithmic type solution. Okay. And then another terminology you'll see sprinkled throughout here using this is those that it's consistent. So in the best case, or like the near best case, you're doing as well as you could possibly do, right? If you had a perfect prediction, you'd always find whether it's in it or not in one comparison. Even in the near best case, it's essentially always going to be constant time. If your prediction error is constant, this is going to be constant. Okay. All right, any questions so far about this? Very nice and easy example. Good. Okay, so the whole reason to go through this is like, well, where are these predictions coming from, or why might we care about this idea of with predictions? And really the sort of motivation for this is, now or some number of years ago, we've been turning a corner where we have these tools, machine learning, which seem to be really, really good at providing us predictions. The way I like to think of it, or the way I like to imagine this, is that I have someone, I'm in a computer science department, I have a bunch of people down the hall from me, and they're saying like, we have these great magic black boxes that can predict things, how can you use them? I'm going to be like, that's great. Let me go see if I can use that to figure things out. So, this is different than how we normally have worked or work in the traditional algorithms and data structure space, right? Which has been based on worst case analysis. And I am not trying to, speak negatively of worst case analysis. Worst case analysis has been fantastic. Very important analysis paradigm. Lets you do things like just treat, algorithms and data structures as subroutines and compose them and still get bounds that make sense. Worst case analysis has dramatically moved theory and practice forward. But particularly when you talk about, people who are building things, they will complain, and with some, reason for doing so, that the worst case isn't everything, right? That there are plenty of situations where, this worst case analysis is getting us to the wrong place. This isn't something new. Theory has, for decades, been trying to find ways to go beyond this worst case analysis. So me, because I'm very interested in randomness, certainly there's been analysis where you look at, say, the input as random. There's smoothed analysis that looks at cases where the input you say is, well, I'm going to assume it has undergone some sort of small random perturbation. There are plenty of algorithms where we look and say, well, we're going to limit the input space in some way to make this tractable. And even, in the sense that approximation algorithms, okay, you typically analyze the approximation algorithms in the worst case, but you're sort of loosening things to not actually get the right answer. So you're beyond worst case in that sense, and all sorts of various heuristics that are motivated by theoretical ideas. And the whole point here is that machine learning is offering us new possibilities for moving beyond worst case analysis by looking at through the lens of, we have these predictions or predictors. There's a whole book, if you want, on beyond worst case analysis. I and Sergei Vasilevsky managed to sneak in a chapter at the very end. Luckily, you don't have to buy the book if all you want is our chapter. You can find it online at the archive. But this hopefully has set the framework for what we're going to be doing here, right? So, or what I want to talk about, which is using machine learning for predictions. Machine learning, for instance, can give us predictions, and given good predictions, can we do better than what the standard worst case analysis would tell us? Okay. And in particular, a question we might have is, well, sometimes, maybe the robots are evil or our machine learning predictions go bad. What should we do even if the predictions are bad? What can we say then? And the point here is not to be, sort of the complaint that I would say rightly theorists have about a lot of machine learning papers, which is like you say you have an algorithm, you've run it on some examples, you've declared victory, but we really have no idea of how it works or why it works or what it would do on the next set of examples. Ideally, we'd like to be able to make some sort of provable statements. Okay? And the provable statements may be conditional, right? It may be the provable statements or something. If you can give me predictions that are X good, I can give you an algorithm that's Y good in return. Okay. And this whole area has been called, you'll hear these two terms of algorithms with predictions or learning augmented algorithms. In fact, Sergey and I sort of took our survey and we briefly wrote up something for the CACM, try to get this in front of a more general audience. And as part of this, we sort of summarized some of these properties that, I'm not always going to call them out explicitly, but hopefully you can keep in mind as we're going through this, right? There's this idea of consistency. When the predictions are good, you get near optimal solutions on a per instance basis. You're doing the right thing on a specific examples. On the other hand, robustness is when the predictions are bad, you're still doing something close to like what the worst case algorithm would itself be doing. Smoothness is the idea that you're somehow interpolating in some graceful way between these two sorts of extremes. And then finally, of course, and this is the part where I often punt on and assume this is for the people down the hall, but there are plenty of people in theory who, have feet both in theory and in machine learning, and particularly a lot of machine learning is based on stuff that has come from theory. Are these things that we're trying to predict actually learnable, right? If we're going to say, well, I have an algorithm that does well if we have these sorts of predictions, can you say, well, actually good, there's a learning algorithm that will get you those sorts of predictions, under reasonable assumptions. So these are the current properties that I think people are converging on and seeing as being very important. But I want to really emphasize that this area is like new, right? Like roughly speaking, the sorts of frameworks that have been coming out roughly in the past 5 years, right? So this is still a very new area, still very, clearly going to be a very active area. So, maybe we've missed stuff, right? So it's certainly a good area for grad students to look at and try and come up with new and fresh ideas. Before I start getting into some more sort of examples or problems, I wanted to point out there's a website. If you look up algorithms with predictions in GitHub, it should come up. That's been tracking the papers. It's sort of an open website. So if you've written papers that aren't up in here, you can go ahead and add them. And it's building a collection so we can, very quickly write our bibliographies for our, submissions to SOTA or Stock or Fox or whatever. You can quickly find the relevant papers, but also, so you can see them if you're interested in the topic. I think the last I saw was like 103 or 104 papers they had up there. Interesting, also, like one of the reasons I think this is an interesting area is I actually, do a fair amount of collaboration with people on the system side. And, as I'll talk about, a good part of this work also comes from the system side. They're very interested in this. They see machine learning also as a way of improving and building systems. So Tim Kraska's group, has things set up with a website that has listings of ML algorithms for systems papers that is also relevant. Okay. Any questions about this before I go on? All right, so I'm going to start by talking about learn bloom filters, and I'll mention some others. We'll see what the timing is. I may get into more details on this in the second hour and just cover the basics here. But let's talk about learn bloom filters. So first off, as Jelani did, maybe I'll ask the audience, who here already knows, and of course, if you know them, you love them, knows and loves bloom filters? It's only about half. Okay, so the half that does put up with me real quickly. I'll try and go through this pretty quick, but just here's background on bloom filters. So bloom filters is a way of what's called approximate membership queries. So we're given a set and we're going to ask questions like, hey, is this an element of your set? Okay, it looks very similar to that binary search example we were just looking at. But the idea is we'd like a data structure that's fast. Ideally, it would be like even faster, potentially than the binary search. And more importantly, it should be small, like smaller than explicitly representing the whole set. So that sort of does away with the whole search idea or concept. And to allow these sorts of speed and size improvements, we have to trade off something. So we're going to allow some probability of an error. Okay. I use these in the undergrad class. I teach in algorithms and data structures to sort of introduce the idea that correctness is, students are used to thinking of time and space as features you can trade off for algorithms. They get that idea. When you sort of tell them that correctness is something that you can trade off, that sort of blows their mind a little bit. That's sort of a new concept for them. So the types of errors we can have are false positives, something's not in the set, but we say that it is, and false negatives. Something's in the set and we say that it's not. Typically, in these cases, we say that false positives, if they occur small enough reason, they're okay. False negatives are bad, right? So if you're thinking of like a listing of, websites that your browser should not go to because they're dangerous, right? You can see that false positives may be okay. Like you're restricted from going somewhere you should, that seems correctable. False negatives would be bad. You go someplace you're not supposed to go to, then your computer becomes virus ridden. All right, so the standard Bloom filter is just a very simple bit array. You start with an array of n bits filled with zeros, and now you get some hash functions you have lying around somewhere, and you hash each item in your set k times. Each hash is going to give you an index into the array, so you can think of it as giving you a value between 0 and n-1, and you set the corresponding bit in the array to be 1. You do it multiple times if needed. Setting it to 1 multiple times will keep it as 1. And now to check if an element is in the array, you're going to hash it those k times. If you ever see a 0, you know this wasn't an element in your set, because by construction, if it was an element in your set, you should have seen all 1s when you hashed it again. Okay. If you see all 1s, you're going to say, yes, it is in the set. That may be a false positive. And I won't go through all the math because it's in things like, my textbook and so on, or various papers if you want to see the math. But you can sort of figure out, based on the fact that this is done by hashing, if you assume random hash functions, you can actually come up with an equation. The key thing is that the false positive probability falls exponentially in the number of bits per item, right? So the more you increase the bits per item, again, it's going to fall very quickly, very steeply with that number. And the other thing is that once you have these equations, you can do fun optimizations. So if I treat the number of hash functions as a continuous random variable, even though it should be integer, right? I can say, okay, well, if I have 8 bits per item, how many hash functions should I use? And both 5 and 6 hash functions are the sort of the low end of the curve. They get you just around 2%. All right, any questions so far? Great. All right, so now we're going to get to the fun and interesting part of the story, which is these guys wrote a paper called The Case for Learned Index Structures, right? And draft of this was going around and people seemed very excited about it. I had sort of glanced at it, didn't quite get it. And I was at a conference giving a talk about something else, and someone, Suresh Venkata told me, it's like, hey, you should really read this paper. Someone from the theory audience should figure out what they're doing here. So I was like, okay. There were parts I hated about the paper, parts I liked about the paper. But what was great is like I actually got them to talk back and forth with me and help clarify some of the issues I had with them, and they helped clarify what it was they were doing, and that really helped get me involved in this. So I'm going to talk first about what they did or what their setup was, because they were the ones that came up with this idea of, well, we can use learning to improve Bloom filters. Okay. So they were saying, yeah, we can do better than standard Bloom filters in a data-dependent way. That is, maybe assuming there's something learnable about these sets that you're trying to represent. And the idea is that we're going to use some sort of machine learning tool to develop, again, what to me is just this magic crystal ball. And what this crystal ball that they said is going to provide is it's going to provide a number which we can interpret as a probability that the element is in the set. Right, so it'll return 0.9, which you could think of as a probability, or more like if you want to anthropomorphize the learning algorithm's belief that the element was in the set, right? So it says, okay, 0.9, and ideally, it should give you few false positives. But remember, for Bloom filters, we don't want any false negatives, right? So how do we take this oracle thing that they're giving and turn it into something that actually looks like a Bloom filter? Okay. So first off, just like how the learning part works, right? The positive elements, you can think of it as a binary classification problem. The elements of the set are clearly positive examples. You can either find negative examples by like choosing randomly, or if again, it was a security site and you were talking about like, bad URLs, you might have a bunch of good URLs you could use as negative examples. And they've said, well, you can pick your favorite learning algorithm, like design a neural network, produce this sort of probability estimate. And then, if you just had this learning oracle, you might choose a threshold. You might say, well, if it tells me, above 0.9, I'm going to believe it, and say, that it is, an element of the set, and below 0.9, I'll believe it and say, yeah, I don't think this is actually an element of the set, or you pick some sort of threshold. And in both cases, there may be false positives, or that you could get both types of errors this way. There might be false positives, might be false negatives. Right, so to avoid the false negatives, what we do is we have a backup Bloom filter, right? So you can think of this sort of diagram. It says, okay, you get the input. If the learned oracle says to accept it because it's above some threshold, then I accept it, right? Okay, maybe that generates false positives. False positives are okay if there aren't that many, right? If it tells me it's not in the set, well, then I better do a double check. And that double check can itself be just a regular Bloom filter, okay? And now the negatives are sure to be negatives. There may again be false positives here, but again, if there aren't too many, okay? So the question is like, well, if you're just using a backup Bloom filter anyway, like what have you gained by doing this, right? Like how have you possibly gained by doing this? And the key is that the backup Bloom filter doesn't have to be for the entire original set. It only needs to be for those elements that are in the set, but that the learned oracle said were negatives, which ideally should be a much smaller collection, right? So the idea is that this backup Bloom filter can be much, much smaller than a regular Bloom filter. And if your learned oracle, whatever space it takes, hopefully it's also much smaller than the original Bloom filter, then you'll have saved space overall and hopefully done so while maintaining the same levels of accuracy. Actually, before I go on to some of the issues, any questions about this picture, the basic idea?
Oh, actually, I have a question. Sorry, I'm on Zoom.
Yeah.
Yeah, so my question is like, if most of the time, like we see positive, in other words, if like this helps, then I'm assuming most elements are positives. But if most elements are positive, then what's even the point of doing the Bloom filter? Because like, if most elements are positive, you don't like save anything by hashing, right?
I'm not sure what you mean by most elements are.
I mean, if most elements are negative, then you have to use the backup filter anyway most of the time, right?
Sure, but the backup Bloom filter is much smaller, right? So let's say our goal is, the typical goal for Bloom filters is how small can I make this at a certain accuracy? So the fact that you have to use the backup Bloom filter, that's not a problem. The question is how big it is.
Oh, so you're saying you can make the backup filter smaller if you use the learned oracle also?
Yes.
Oh, I see. Okay, sounds good. Thank you.
Okay. Right, but you brought up an excellent point, which is like, well, maybe this is slower, right? Because you're going to have to do some sort of prediction, right? What's the running time of the oracle and so on. And agreed, like those are questions that may be important in practice, right? But typically, when you're looking at Bloom filters, the question is like, what's the size versus the accuracy trade-off? And the running time may matter depending on what your application is, but at the moment, we're just thinking, at least right now, about the size versus accuracy trade-off.
So we are, for example, allowed to go through all the elements.
We're allowed to go for?
Through all the elements depends. Let's say you learn this oracle, and then afterwards, after you learn this, you test it on all the.
Right. So the question was, right. So the question is like, yeah. So what work can we do setting up the learned oracle? Well, yeah. So I'm assuming that you're doing all this in advance. This is for, I guess, a static set. So it's like, yes, you have the set. You do the learning, you figure out which of the things are negative, so you can create this backup Bloom filter. All of that doesn't count in the cost, that's just setup. And then the question is, what's the query time? And again, you're asking good questions. In some applications, you may be like, well, I'd like it to be updatable, and we'll leave those questions aside. Or you might be like, well, how long is this training time? Because that's important. Like, at the moment, at least, we're leaving that aside. That we have does streaming make sense? So a stream of queries. Possibly, but most applications, like, again, so think of, again, the security setting where it's like, I have a list of bad websites. I don't actually want to keep a list and somehow do a search of all the bad websites. I can use a Bloom filter instead, knowing that I may have some smallest chance of false positives, right? You know, in security systems, they have the set, they do it. They may send out updates, but they do, you know, they refigure everything out and send out like, you know, once a week your security thing, software updates. Yeah. I can't even hear you.
The question is, what is Oracle?
The Oracle is like so that's just how I'm describing the learning algorithm, the predictor, right? Because to me, you know, I could have called it magic black box, right? Someone down the hall has come up to me with the crystal ball and it says, you give it, you know, in my example, a website and it will spit out a probability that it thinks, you know, it was on the bad list. Anything else? Okay. Right, so, you know, one of the things that's worth noting, and this was a back and forth I had with them about the paper, is, you know, the notion of false positive between the regular Bloom filter and the learn Bloom filter is actually quite different, right? So you can call them both false positives, but they sort of mean different things. So for a Bloom filter, the false positive probability, you know, you can calculate is the probability that just any non-set item yields a false positive, right? Whereas for the learn Bloom filter, you know, what they call the false positive probability is actually an empirical estimate. And it's based on assumptions like that the data you trained on, particularly the data you trained on maybe to get an estimate, is going to be the same as the future data that you see, right? So it's their notion of what a false positive is very data dependent, and it may not be suitable for various applications, right? And so you may ask, well, if the data starts to change, what should I do? You know, the answer I think they give is to, you know, retrain and ship out a new Bloom filter, right? Again, you have to look at if that's reasonable or worthwhile in various applications. So an example of this is like, you know, and might be good just for thinking about how we understand this anyway. Suppose your universe is the numbers from 1 to 1,000,000. Your Bloom filter is supposed to hold 500 random keys from 1,000 to 2,000. You can imagine what your learn predictor might do is it just might say, oh, well, you know, I'll accept all the keys from 1,000 to 2,000, right? I don't really have a way of, you know, deconstructing this random set in this interval. So I'll just, you know, treat it as the whole interval because I can't really learn the random behavior in this range. And now, you know, what the false positive probability is would depend on what your queries look like, right? So if you trained over queries being uniform over the whole space, you know, your false positive probability would look quite low, right? Because you're just not hitting that range that often. But if all of a sudden you say, oh, well, the queries are only over 1 to 100,000, not 1 to 1,000,000, you know, now your false positives have gone up by a factor of 10, even though, you know, nothing's changed, right? So it's a sort of a different notion of false positive here. Now, one of the things that was interesting is that like they suggested this learn Bloom filter and did experiments, but they didn't really analyze it. And so this is what Peter was alluding to. I was like, hey, I bet you can analyze this, right? And it turns out not to be like once you frame it, it's not really that hard. You know, you need to keep track of various variables, you know, the size of the set, the size of the learned oracle, the false positive and false negative probabilities, and so on. You know, and I won't go into the details, but you can come up with equations for what the false positives of these things look like. And one of the interesting things or outcomes of this is that, you know, a learn Bloom filter is actually better under some conditions, okay? And the condition is like this X over M ratio is smaller than something. What was the X over M? You know, it's the size of the learned oracle versus the size of the set being stored, okay? So if we imagine like we were trying to keep track of a set like, you know, perfect squares up to 100,000, and then perfect squares up to 1,000,000, and perfect squares up to 1,000,000,000, right? If we think of some way of these sets growing asymptotically, right? If we have some sort of succinct representation of the squares, or the learning algorithm can come up with some succinct representation of the squares, then the idea is that if that's the case, then we would expect x over m to go to 0, right? That the representation that our learning algorithm is coming up with is growing faster or growing smaller than proportionally with the size of the set, then this will go to 0, which will mean that eventually, for some version of the problem, right, as you get big enough, the learn Bloom filter is going to have to be better than the regular Bloom filter, which is an interesting way of thinking about it. So it's saying, like, if your set is learnable in this sense, then yes, learn Bloom filters will be better, at least eventually. All right, so conclusion thus far is that learn Bloom filters can indeed be better than regular Bloom filters, assuming that they're structured sufficiently that you can get a good model for the data, right? And again, we've already talked, where it's come up in questions, that there's a lot of like, well, in practice, what about this? What about this? What about this? And like, these are all things to be considered for sure. But important thing here, I think, is to just get the basic structure idea. All right, so a bit in the second hour, I'll sort of leave till then. There's actually a improved version of this worked on with some people, my student and Tim Kraska and his student, Kapil Vaidya here at MIT. The idea is that we're not really using the score particularly well if we're just setting a single threshold. So if we allow ourselves to use multiple thresholds or do things that are more based on the score, can we do better? And in fact, we can. We show how to analyze this sort of tuning and come up with the best sorts of results. All right, so the summary, I guess, so far is predictors can actually be very helpful to enhance data structures, which I think is a fantastic idea and really great. And let's give some other ideas and examples of learning. And so here I'm going to try and take a break and do something that I don't often do, which is stop talking about myself and talk a bit about some of the work of others. Frequency estimation with prediction, right? So Jelani was alluding to this earlier in his talk. He mentioned or saw on the slides there count sketches, right? So there are various ways of doing approximate counting or frequency estimation, right? So you have an online data stream and you want to say, oh, well, how often has this appeared in the data stream? And you don't want to keep counters for everything because that's going to take too much space. So in some sense, very similar to Bloom filters, there are these various hash-based techniques. For instance, the count min sketch, hashes each item into some number of counters and increments the counters accordingly. The problem is there are going to be collisions, so multiple things might hit the same counter. So the way you deal with this is you take the minimum of the counters and assume that's a good estimate. And there are various provable things about that. How many people have seen count min sketches before? Yeah, pretty much everyone. That's good. Okay. Right, so the problem with sketches is that these collisions can cause you to miscount. And sort of the worst case things under at least certain error measures is, if you have a low count item that's going to return a very, very high count because somehow all of its counters include one of the high weight, high count items, right? That would lead to a huge error, which would be very problematic. So if you could somehow, and this I think, I don't want to speak for Peter, but his group had this great idea. It's like, if we could just remove all these high count items to begin with, right? Then we'd have a nice, pleasant data structure. All the counts are low, the amount of noise wouldn't be that bad. Things would be very accurate. So if we just knew what these high count items were ahead of time, and there can't be too many of them because they're high count. So there just can't be too many of them. If we knew what they were, we could just pull them out and actually count them and leave this approximate structure for like the long tail of low count items. And so, well, we can't just magically know what are the high count items, or maybe we could, because that machine learning person down the hall, that machine learning person down the hall comes up to us and says, hey, I have this great crystal ball for predicting what the heavy items in your data stream are. Like, oh, I can use that, right? And so they did, right? And they said, and again, one of the things I like about this is you can, so the mental picture is just this very simple diagram, which says like, okay, an item comes in, do I think it's one of the heavy items, in which case I'll put it in its own bucket. That means I'll just, count it by itself. And if it's not heavy, I'll throw it into the sketching element. And as long as I'm right most of the time, I should get much better results. And, I won't get into the details, but they show it's like, yep, we can actually prove things like that you can get better results doing this. And not only can you prove that you get better results, but you can also run it and get better results. And again, I'm not going to get into too much details about the chart, except to say, like, these are charts where it's like accuracy versus space. So left and down is better. And if you look at the charts, they'll say it's like, yep, once we throw in this learning, we do better. We get more down, more left, right? We're able to be more accurate with less space. Okay. Another online problem example is caching. Okay. So caching is one of the initial important standard online algorithms. One of the first one I remember learning about in grad school. So the simple theoretical model is all items have size 1. You have a cache of size k. Elements arrive one after another. And if it's in the cache, you pay 0 for getting that element. And if it's not in the cache, you have to pay 1. And your goal, of course, is to pay as little as possible. Okay. And when an item comes, you can decide whether or not you want to keep it in the cache. But if it's in the cache and your cache already has k things, then you get to pick. You have to figure out what you're going to throw out. Okay. So the optimal offline algorithm, called Belladay's rule, is that you should always evict the item that's going to appear farthest in the future, right? So if this wasn't online, if you knew the data stream makes sense, what should you kick out? The one that's furthest out. Okay. Now, the problem is, of course, we don't know the future, but there are those machine learning people down the hall. They like to predict the future all the time. That's what they think their job is. So you go ask them, and they come back with a crystal ball that tells you something, gives you predictions about about when the next time is you're going to see the element. Okay. Right. So this was worked a couple years ago by Lacourse and Vasovitsky. So for every arrival, just try and predict the next time it will appear. So you have sort of one prediction for every element you have lying around. You can consider the absolute error. And again, your goal here is to have something that's consistent and robust, right? The competitive ratio is very small if the error is 0 or near 0, and it's robust. I'm saying it's a nice function of the error, but in particular, even if you get really bad predictions, you're still going to be okay. Okay. So the first thing you might think of is just like, well, let's just follow the predictions, right? Evict the element that is predicted to appear furthest in the future. Okay. And this probably does okay in practice, depending on your predictions, but at least in theory, it can be very bad, right? And sort of, there's a very easy, but don't worry if you don't get it on the fly, because it's hard to see things on the fly, but a very easy bad example, right? So if you have some element A, right, and your element A is supposed to come like right away, whatever that means, but it doesn't. And then you have B and C, which are 2 other elements, and the elements you have for that are good predictions. It's like, yep, that's coming next. Yes, that's coming next. Yes, that's coming next. But if you think you're supposed to hold on to A because you think A is coming, then A will be kept in the cache and B and C will just alternate. So you're always throwing out the next thing to come in because you're following your prediction a bit too closely. All right, so their suggestion was to use predictions to enhance an existing competitive algorithm, namely the marking algorithm. How many people have seen the marking algorithm? It used to be like, again, sort of the standard, maybe online example in grad school. Fewer than everyone. So the marker algorithm works in phases, right? So the idea is you start a phase, all the cache entries are unmarked. When it's time to evict something, you pick a random unmarked entry, throw it out. And so when an element arrives, you put it in the cache and you mark it. So eventually all the entries in the cache are going to get marked and you start all over again. Okay. And this avoids the A problem in some sense, right? Because after a while, after some amount of time, everything gets marked and you start all over again, everything's fresh and has the potential to be kicked out. So the marking algorithm is known to be 2H of K competitive. H of K is that golden ratio thing. The 1 over 1/2, 1/3, 1 up to 1 over K, which is approximately log K, right? So 2 of HK competitive. So they said, well, let's just change that. Let's figure out the marking algorithm with predictions. So when it's time to evict, instead of throwing out something that's random, throw out the entry with the prediction that's farthest in the future. And then they analyze this. Okay? And I won't get into their analysis, but it's like, if you have perfect predictions, this is going to be too competitive with the optimal. So again, not too much worse than the optimal. That's one of the things we want. And they point out, and this is something you could probably do in a bunch of algorithms, that if your predictions seem to be going wrong and you're getting performance that's not what you expected, you can just say, forget it, I'm going back to the regular marking algorithm. And essentially they show that you figure that out after a small enough time. So that's the 2 plus epsilon log K type result, right? Instead of, because the original marking algorithm was roughly 2 log K, they get a bit worse than that. And they show that this works, even with very simple predictions, they can do better than things like LRU in practice, at least recently used in practice. Okay. There's been a bunch of later work on this under caching, but also, I spent the last few years, they've been doing things like putting me on machine learning committees like ICML and NeurIPS and stuff. And I read a bunch of these papers. Like there are tons of papers coming out about revisiting online algorithms under this scenario. So, pick your favorite online algorithm. You can check if there's already been a paper on this. If not, you can write one. People have been really looking at this and coming up with, I think, some really neat results. All right, so summary of that little piece. Online algorithms are a good natural place for these sorts of algorithms. And this is like sort of a very quickly current growing area of research. Any questions about this? Yeah.
I was wondering, is there any further question about how to measure, what is the best way to measure the error or predict this, sort of the parameter that inform your hardware or hardware ratio is? Because I was thinking for that kind of example related to this DCDC, if you something more like the versions, so how would it be able to map that all way or never come up? In my mind, it's kind of like that.
Yeah. Right. So the question is, is there some sort of idea or science or, how do you figure out what is a good thing to predict, right? Because ideally you'd like to tell the machine learning people like, oh, this would, can you predict this for us, right? Or this is the sort of thing we want from our prediction. And I'd say I don't think there's anything general, things right now are a problem by problem basis. Right, so instead of thinking like, one way of thinking of the caching thing is like saying, instead of predicting when it's next going to appear, you sort of like predict the remaining time or something until it appears. And then if that passes, it should get reset or something. So I wouldn't say there's anything systematic per se, but I think like that's clearly an important question and deals with sort of the aspect I talked about before about learnability. Like one of the things you'd want is like, hey, if I'm going to say I have a really great algorithm, if I predict this, maybe you should care about, but is that something that's actually predictable in any reasonable sense? Yeah.
Eric, the work that we create on the static oracle, like since we're in that online application, maybe we get the oracle to be online.
So the question is, like, could the oracle itself be online? So I think some of the works, and I think particularly the next thing I say, is at least related to that idea. Yeah, it's sort of an interesting question. What to do, like learning as you're running the actual algorithm, and that can depend a lot on things like how fast your algorithm learns compared to the cost on the examples you're doing, and sort of how dynamic or how static they are. But I'd say that's mostly an open area. All right, so for the next part, and I'm very sad to be doing this online, I wanted to add a bit new to this, like I've given this talk in other places. We just had a workshop at whatever the summer was, Stock or Fox, whichever one it was. Stock. They're interchangeable to me. And I liked one of the talks. So to be quite frank, I just stole like half a dozen of Ben Mosley's slides without asking him. Sorry, Ben. So the next few slides are covering something called warm start. And again, literally, I just kind of stole a few slides from him. This is based on his joint work. I really enjoyed his talk at the workshop about this and wanted to present this idea. All right, so this is the idea called warm start, okay? So the idea here is like, if we think of a problem with worst case analysis, the way Sergey has this great description of it, where it's like, we're like Dory and Nemo, right? It's sort of like every time we solve a problem, it's like, oh, problem. Like, and then it's like, someone comes to you again, it's like, oh, problem. And it's like, you've never seen that problem before, right? It's like, every time it's fresh and new. And that's sort of a weird way to think about things in practice, right? Because in many cases, you're solving repeated problems on similar instances, right? So like your scheduling problem, if you're scheduling like, pilots on airplanes and things like that, often your scheduling problem for one day is going to look very similar to the scheduling problem you had on the previous day. And yet in worst case analysis, we always sort of start directly from scratch, which is a little weird. Now, the problem obviously is like, well, okay, you want to take advantage of similar instance, like what does similar mean? Like, how are we going to formalize that or in a way that we can actually study? Okay. And this is where, we can think of machine learning helping us, right? So, a model we can think of is that we have repeated problem instances drawn from some unknown distribution. What we'd like to do is compute some sort of starting summary for our algorithm, right? Based on these previous examples or based on what we've learned from the distribution, and then design an algorithm that goes faster when given this sort of starting summary. Okay, so these could come about by like machine learning, right? So the machine learning might, however, be imperfect, right? There might be issues. So like, maybe the warm start is giving you a starting hint, like start your solution here, but the place it's telling you to start isn't even a feasible solution for your new problem. It may be that it's not actually useful, that it sort of leads you the wrong direction. We have to be careful to pick things. Ideally, we pick things that actually are learnable. Okay. So the example problem they were looking at for this is weighted bipartite matching, right? So you're given a graph, bipartite graph, a left side and a right side with edge costs. You want to output the minimum cost perfect matching. And in their version of the problem, the left and right sides, they stay fixed, but the edge costs update for each instance, right? So the edge costs might get updated. And the question is what to predict. And so you can set this up as a linear programming type problem, and then you can look at the dual problem. And the Hungarian algorithm, and I'm not going to get into too much of the details of this, starts with the dual values at 0 and sort of increases the dual values, tightening up constraints, and eventually comes up with, an ending matching through the solution. Okay, solving the LP by actually looking at or solving the dual problem. Okay, so their idea was like, well, let's use the previous problems to predict the dual values as the starting point. Okay. And again, I'm just going to point you, say you should look at their stuff. I just swiped these slides, but they're able to prove things that you have to be a bit careful because the dual solution that if you start with a predicted dual solution, it might not be feasible. So you have to do something to cut it back to a feasible solution that you can start from. But then if you do that, you get something that is faster because you're sort of starting from a better starting point. And this seems like a good useful paradigm for how you might be able to use learning in a different way to help you improve various algorithms. Okay, any questions so far? All right, I'm probably not going to finish this next part, but I'll try and go only about 10 minutes to 3:05 so we get a break. But now I'm going to switch off talking about other people's stuff, which is so much work, and go back to, much more entertaining stuff. We just talk about the stuff I've been working on. And so for now I'm going to talk about some of the work I've been doing in using predictions with relations to queues. Or you can think of it as, if you like, you can think of it as just regular scheduling. I tend to work on the sort of scheduling problems where people enter and leave and come according to a probabilistic process. Okay, so the standard queuing model that CS people don't take queuing theory unless you live in England or certain parts of Europe. But for other people, this is CS, is queuing theory, where you have some arrival process. Typically, it's what's called a Poisson arrival process, which mathematically means you have exponentially distributed service times. You can think of it as being memoryless, the amount of time you've had since the last customer arrived doesn't affect how long it is till the next customer arrives, right? It's just they're coming in at some rate, but at a sort of memoryless rate. Okay, and similarly for service times, you might have some distribution on the service times. And again, a typical model in theory is that the service times are exponential. That's mostly because math always works out much more beautifully if you have exponential distributions because they're memoryless and you can use that to advantage. In practice, usually the distributions for job sizes are heavy-tailed, right? There's a small number of jobs that are huge and a large number of jobs that are much, much smaller. And in most models, again, the service time tends to be unknown, right? And if the service times aren't known, then this is why in a typical, when you go stand in line pretty much anywhere, airports, I've been flying again, so you stand in line in the airports, they don't do a particularly good job in trying to say, oh, are you going to be quick or slow? It's because they don't trust you, they don't know, so you just wait in line, first in, first out. Okay, but there's other things you can do. And again, one question is also there are preemptible and non-preemptible systems. We'll talk about that in a bit. So the standard result for what are called MM1 and queues, M stands for memoryless. So that says exponential service times, exponential arrival times, sorry, other way around, exponential arrival, exponential service times, and a single server. And if you have first in, first out queues, and the arrivals are of rate less than 1, and we'll just scale things so the service times are mean 1, then the steady state time in the system is this beautiful equation of 1/1 minus lambda, right? So this has this, hopefully, if you haven't seen that before, this 1/1 minus lambda gives you this nice sense of like why the time you spend waiting goes up hugely as, roughly the amount of service available equals the rate at which work is coming in, right? As lambda gets close to 1, you get this very asymptotic blow up in the service time, which is what like people at the supermarket counters or the airline counters, right? They want their people busy all the time, but that blows up the waiting time. Okay. Now, of course, you could do a lot better if you knew the service times, right? So if you knew the service times, you did some version of the shortest job first, right? So, the shortest job first typically refers to the non-preemptive policy, where just whenever a job finishes, you take the shortest jobs that's out there. Shortest remaining processing time lets you preempt. So like if a new job comes in and it has smaller time than the job that you're serving, you say, sorry, you have to wait. Preemptive version of shortest job first. Again, that doesn't look at the remaining processing time, just the processing time, but that's a preemptive version. And like all of these things have been around for a while, and the queuing theorists have figured out these formula for Poisson arrivals and general service distributions. So, I kind of got into this because of that Learn-Bloom filter paper, and I was sort of curious as to it's like, oh, well, okay, well, what would we do if we had predicted service times, or what can we say there, right? Because, it makes a lot of sense that maybe, for your call centers, or even when I'm going to the airport line, someone asks me a question and they can predict, something about how long I'm going to spend in line. And, so then you can think of policies like shortest predicted job first and shortest predicted remaining service time and so on. Okay. And so to start with, again, because I tend to work on probabilities, for me, what this meant is now I was going to consider service times to be like two-dimensional, right? So it's like there's an actual service time and a predicted service time, but they are going to be governed by some sort of probability distribution. So, again, I'm not going to get deep into math, but it's sort of like for shortest job first, you can calculate things out to come out with the expected waiting time for jobs of a particular service time, then integrate over service times to get the total expected waiting time. And it turns out that the important quantities are like the total rate of work coming into the system. And then for shortest job first, right, if my job size is X, I don't care about jobs bigger than X because they're not going to affect me, right? I'm sort of blind to them. It's like they aren't even there, right? So the other quantity that's important is the rate of workflow for jobs with service less than X, right? Because if I'm a job of size X and I'm sitting around waiting, the only jobs that are going to affect me is if a new job comes in with a smaller service times. So those quantities turn out to be important, and you can do an analysis and come up with like this equation, which tells you what the expected waiting time for a job of size X is. And I was a bit surprised to look around because I would have thought someone had done this and said like, well, what do you do for predicted service times? But it was one of those fortunate things that no one had written it down. So I went back and figured out how to, that you could go back and modify these arguments. And now, the problem is instead of having like one-dimensional type integrals for these quantities, you have two-dimensional integrals, right? The important things are, again, the rate of inflow of work and the rate of inflow of work for jobs that are going to have smaller predicted time than you, because they're actually, even if they're bigger than you, if their predicted time is smaller, they're going to get in your way. And you can go through and do the calculations and you come up with very similar looking equations. And I did the same for these other sort of natural systems too. Whoops, I went too far ahead. Good. All right, and then I did a bunch of simulations just to see how things work. So like on the left side here, it's the shortest remaining processing time, and then the shortest predicted remaining processing time. That's it with the predictions, and then FIFO, and then same for shortest job first. sort of focusing on the left, I think the key things that come out of the simulations, like, first of all, it looks like my equations were right, because like the results I get from the equations are within like, much less than 1%, generally like within 0.1% or so of the simulations, which is good. Yeah, so that made me feel a bit more confident. But the other thing is just that like what you might expect, which is that if you're using predictions, here I was using a prediction model where like if your true size was 3, then your predicted size would be also exponentially distributed, because exponential distributions are just fun and easy to work with, would be exponentially distributed with mean 3. And like the key is that particularly as the arrival rate gets large, with predictions, you do a lot better than FIFO, right? You don't do as well, of course, as if you had complete information, but you get an awful lot of the way, even with what I think is not a particularly great prediction idea, right? So, so to me, this is good. Like it says, predictions are good. Let me finish up with this section and then we'll take a break. One of the things I looked at next was what if you only got a single bit hint, right? So a single bit would just correspond to like your algorithm, your predictor just tells you, I think this job is short or I think it's long, right? So you could model that as like, is your predictor, your predictor is predicting, is this bigger than some threshold or smaller than some threshold? And this works out nice for queues because what this corresponds to naturally is like, well, if it's short, you get to go in front, and if it's long, you get to go in the back. Okay. Also, it's a very natural model, so it may be an easier prediction problem than trying to predict exact times. Maybe easier to implement because you're just doing front, back of queue, and so on. Okay, so again, the single bit model is the predictor is going to say if you're above a threshold, you're big, below it's small. We can consider perfect single bit hits are from predictions. And so I derived, these equations. I must say some really fun mathematical expressions popped out of it, which are worth looking at that I won't get into here. But again, sort of with, here I'm looking at single bit predictions when you're using preemptive or non-preemptive versions. On the left is like with perfect single bit information. On the right is with predicted single bit information. And in the middle is sort of the gold standard of shortest remaining processing time. And again, you sort of see, and on the right is, shortest predicted remaining processing time. And again, the point is that like, even with a single bit prediction, you get pretty far along the way. With reasonable sorts of predictions. And this was with exponentially distributed service times. If you have, here I used a model called Weibull, that's a sort of standard heavy-tailed service time. For heavy-tailed service times, the gain are even bigger, right? Because the point is with heavy-tailed service times, you can get these, if you're just using something dumb like FIFO, you get a big job stuck at the front of the queue blocking everyone. That increases the waiting time for lots of people because it sits there for a long time. Again, if you've ever been in line anywhere, you've probably experienced that. And so like with heavy tail distributions, the gains are even bigger. Okay. One or two more slides and then we'll take the break. A problem with using predictions, like if you're doing predictions and you're using like shortest remaining processing time, right? There's sort of an obvious problem, which is that like you say, okay, I predicted this job takes, 2 minutes and it actually takes like 100 minutes, right? And so you run it for 2 minutes and it's expected or its predicted remaining processing time at that point is 0 or starts to become negative, right? So then it is going to be stuck at the front of the queue, right? Nothing's going to get around it, right? And it was sort of clear to me, like when I was first doing these works, I was like, okay, this is a problem, but I'm just going to be like writing equations. I don't quite know how to solve this problem. Like this problem, we'll come back to this. It's clear we should do something, okay? But I'd like to do something like good and clean and distribution independent, and it's not like, well, if you know the distribution, you magically decide to do these sorts of things, right? And I didn't know how to do it. until I managed to work with some graduate students. Actually, Ziv just graduated and will be a FODSI postdoc here next year. Isaac is going to graduate and maybe hopefully also will be a FODSI postdoc if we can get him. And so, I'll talk about how we deal with that problem. Maybe that'll be our starting point after the break.